In this section, we discussed the main theory of the existence of solutions of systems of two first-order linear ordinary differential equations. Now, a system of two first-order linear ordinary differential equations in general can be written like this. So you have x1 and x2 are the two functions that you need to find, are the two differentiable functions that you need to find. And then you can always solve for the derivative of one of the functions and write the equation like that, and then solve for the derivative of the other one and write it as your second equation like that. So the system is going to look like this. x1 and x2 again are the two differential functions that you need to find, and the functions are functions of t. So you see a11 is a function of t, a12, etc. So these are functions of t. Sometimes some books will write it in a way that looks a little bit more readable. So they might use x and y for the functions instead of x1, x2. And also you may omit the t, which is an independent variable. And in that case, the system might look like this. X prime equals a11 x plus a12 y plus t1 of t, y prime equals a21 x plus a22 y plus d2 of t. So if you look at that, that's if you're using x and y for x1 and x2, the system might look like this. And even perhaps you might simplify it a little bit more. Instead of using a11, a12, a21, and a22, you can use a, b, c, and d. And in that case, the system might look like this. X prime equals ax plus by plus y1, plus g1. And you can just leave the g1, you can leave the t out of there. And y prime equals cx plus dy plus g2. And again, you don't have to write the t there. So even if you get rid of it, it may look a little bit simpler. So you see, now that right there, that looks a little bit more like a type of linear systems that we're used to from college algebra. It looks more like it is more reminiscent. But anyway, in general, you use indices, at least in this book, and also because when you use indices, you can more easily translate things into matrix form. And then once you have it in matrix form, then that can be generalized to matrices of any order, of any size. So it helps to treat basically any size at the same time if you just do it in terms of matrices, because the size of the matrix becomes irrelevant. So you could have a system with 3 differential equations, 4 differential equations, 5 differential equations, and it will be all solved the same way. Now, we're going to be concentrating only on systems of 2 differential equations, that are linear, and in that case, we can write it like this. Okay, so suppose that this is our system. First thing I'm going to say is that actually the general theory of two first order linear ordinary differential equations closely parallels what we already know about single linear differential equations of order 2. So basically, it behaves very, very similar. Um, and many of the things that we already learned show up in this case as well, so it can be generalized. So to describe the system more efficiently, we use matrix notation. So if you use matrix notation, if you remember how we do that, if suppose it's our system, then you can write this like this. So you can write, let's say, write them both at the same time. It would be x prime, y prime. That would be the left-hand side of this system equals, and then you can write this as a, b, c, d, and then you can write x, y, and you can see that if you multiply this matrix by this vector, you get ax plus by, cx plus dy. So ax plus by for the top, and then cx plus dy, and then plus g1, g2. So you can write the system like that. Now you can then simplify this further by writing, suppose big capital X for xy, and then writing capital A for the matrix, and then perhaps G, what letter did I use? Yeah, G equals G1, G2. Then using these letters now, this system is going to look like this. X equals A, no, X prime. The left-hand side is X prime. If you take the derivative of X, big capital X, X prime will be X prime, Y prime. So X prime equals AX plus G. All right, so that would be this system written in matrix and vector notation. X is a vector, so if you write capital letters, you can understand that that's a vector. But some people also write just the arrow to remind themselves that that's a vector. And also for the G, that's a vector. It has only two components. So the system can look like this. All right, so in general, you can do that when the system is this, and then the A will be the matrix coefficient A11, A12, A21, A22, and so on. And then the X, instead of being XY, like we used here, the X will be X1, X2, because again, we're using the notation in the book, and that's what they use. X1 and X2, because that's more easy. That's easier to generalize when you have multiple equations, x1, x2, x3, x4, etc. You have more dimensions. All right, so then if you introduce that notation, x equals x1, x2, and then g equals g1, g2, and then a equals the matrix of coefficients, then you can write this system like this. All right, and the use of vectors and matrices not only saves a great deal of space, but it also facilitates calculations and emphasizes the similarity between systems of equations and single equations. Because now that looks like a single equation, so it emphasizes the similarity. Okay, and then a solution of this system is just going to be any vector function like that, which in reality, right, it is, once you find this vector function, you are finding the two functions that solve the system. So in this notation, once you find capital X, that means you're finding the X and the Y from this system. You'll be finding the X and the Y. You'll be finding X and Y. Okay, so you'll be finding the two functions that satisfy the system. So well, we can just say we're looking for the vector function because that will find both at the same time. So we're looking for the vector function that satisfies this equation. And of course, the components, as I said, x1 and x2, satisfy the equations of the system. So that would be the actual solution. All right, how do we know that a solution to a system exists and is unique? Well, this theorem is very similar to the theorems that we have already learned. Basically, when all of the functions involved are continuous simultaneously on the same interval. So you would need all the entries of the coefficient matrix, the matrix of the G1 and G2. I mean this G to be continuous, which means that G1 and G2 are continuous. So the non-homogeneous term. So all of them have to be continuous. So in matrix notation, that would mean that this is continuous and that is continuous. Basically, again, everything involved except for the x that you're looking for. Everything else if it needs to be continuous. So if everything is continuous on an open interval, then a solution is guaranteed to exist. A unique solution is guaranteed to exist that satisfies the initial conditions. And look at the notation here used in the book. Is kind of new for us. So the notation they use in the book is you need to know the value. You need to know the value. Right, we're looking for this. You need to know the value of that at a particular point. And then in this notation, it will be x naught of t, y naught of t. So you need to know that. So the notation, and this is a particular point. Oops, let me write that again. This is at a particular point. So this is x t naught y t naught. Okay, there. There's a mistake there. And then when you use the notation instead of this notation, when you use the notation x equals x1, y1, in the book they use, right, so let's say we plug in at t naught, this would look like x1, oh sorry, this is x2. So x1, x2, this is going to be x1 evaluated at t naught, and then x2 evaluated at t naught. So you need to know what this is. And then the notation they use in the book is x1 0, and that's not an exponent, okay, this is superscript, and then x2 0. Okay, why they use that notation, I don't know. That's the book's notation. So basically, we need to know that this, the initial condition is going to look like this then. X naught 1, sorry, I wrote that backwards. X1 and then 0, x2, 0. So then, but what is that? This is this. So then, these two are equal. So it's going to be like this. X1 t naught equals x1 naught, and x2 t naught equals x2, and then the naught. So, it's kind of weird, but this is the way they write the initial condition. When you spell everything out, okay? When you use vector notation, it's kind of easier. You just write x t naught equals this, and that's it. It's kind of easier to read, but anyway. So if you have an initial condition on that interval where everything is continuous, then a unique solution is guaranteed to exist throughout the interval. So this is basically just the same as a single equation case. Everything needs to be continuous on an interval that contains initial condition. All right, and then we also have this principle, this theorem that says, we already seen this too as well in the single case. If you have two solutions of a homogeneous system, it has to be homogeneous, meaning there's no G or the G is 0, then any linear combination is also a solution of the same equation. If you have a homogeneous system, if you have um, two solutions, then any linear combination is also a solution. All right, and then the Wronskian, we already have seen that concept before. In this case, the Wronskian, if x1 is a solution and x2 like that is another solution, then the Wronskian, okay, if x1 of that is, these are solutions of this, then the Wronskian of x1 and x2 is going to be basically you just write all the entries in there in order, and you can write them as rows or vectors, it doesn't matter. You get the determinant of that, that's the Wronskian. And as before, very parallel to the theory of single equations, if you have two solutions and the Wronskian is non-zero, then these form a fundamental set of solutions, meaning the general solution is going to be then C1 x to the 1 and then C2 x to the 2. That would be the general solution. So this is all like before. And that's it. That's a summary of section 7.4. Now let's go over section 7.5. So recall then that we just talked about this. The general system of linear ODEs with constant coefficients can be written in this form. Okay, where A is a matrix with constant entries. When G of T is 0, as I mentioned just a little bit ago, the system is called homogeneous. When G is not 0, then it is non-homogeneous. So we're going to focus on the homogeneous case. So G of T equals 0. So suppose we have this system. The system is going to then look like this by omitting the T. So is that, but omitting the T is just going to look like this. All right, so here's the theorem on how to solve these systems. And before we get to the theorem, I should say there's several methods for solving systems. All right, and unfortunately, because we're running out of time this semester, this coronavirus messed everything up. We're only going to be looking at one method. Okay, that's it. We don't have time for more. But there's three methods that I usually cover in this class for solving systems of linear equations like this, of linear differential equations. One method is using linear algebra, and that's the only method we're going to have time to discuss. This is the method where you solve the system by finding eigenvalues of the matrix and using them to write down the solution. So using eigenvalues. Then there's two other methods that we are already familiar with. You can adapt them to systems. You can use the Laplace transform to solve systems as well. In that case, I mean, this is not hard, but we won't have time to do it. In the case for the Laplace transform method, you basically take the Laplace transform of both equations, and then remember that the Laplace transform the problem into an algebraic type of problem. So you take the Laplace transform on both equations, and then you take it from there. And then there's also a way to adapt the method of variation of parameters to come up with a formula that solves the system. And this method actually works also, I mean, both of these methods work for easily, just without any modifications whatsoever, for the methods in which the system is not homogeneous. So that's an advantage. And also, um, the size of the system does not matter. All right. So if we had time, we would cover these as well, but we don't have time. So we're just going to concentrate on the linear algebra method. Okay. All right. So that's I wanted to say that. So using the linear algebra method, this is how you solve a system like this. We're going to find the eigenvalues of A. We're going to find the eigenvalues of A. And just like in the single case, when we were solving differential equations that were linear with constant coefficients, we found, so the analogous in that case was like finding the roots of the characteristic equation. The eigenvalues, remember, are also the roots of a characteristic equation. Is a characteristic equation of the matrix, which is the determinant of A minus lambda I. So the eigenvalues lambda 1 and lambda 2 are still the roots of the characteristic equation, which is now in this higher dimensional context we call them eigenvalues. But in that case, in the single equation case, once we found the roots of the characteristic equation, right? So we had r squared, I don't know, plus, well, ar squared plus br plus c equals 0. We found, once we found the roots of that, we had three cases. We could either have both solutions are real and different, both solutions are real but the same, or both solutions are complex. And again, because we are running out of time this semester, we are only going to focus on two cases. The third case, if you're interested, you can read it on your own. We're only going to be doing the real and different and the complex case. If you have time, you can read the real repeated. Fortunately, we don't have time. Okay, so here's the real and distinct eigenvalues or roots. Suppose you found those, the eigenvalues, then you're going to find the corresponding eigenvectors. Okay, the corresponding eigenvectors are x1. This is the corresponding eigenvector for lambda 1, and this is the corresponding eigenvector for lambda 2. Then the general solution, we can immediately write it down. And the general solution is going to be x equals c1 e to the lambda 1 t times the corresponding eigenvector plus c2 e to the lambda 2 t times the corresponding eigenvector. And that's it. That is the general solution. So basically, it's a linear algebra exercise where all you have to do is find the eigenvalues and eigenvectors. Once you find eigenvalues and eigenvectors, you're done. You can immediately write down the general solution. And remember, this is for the homogeneous case. There's no g's there. All right, so with that said, let's do our first example. Find the general solution of this system. Okay, this actually is a matrix, so I'm going to call that matrix 3, -1, 4, -2. This is a matrix that we already found the eigenvalues for. This was in the previous lesson. And it is this one from a previous lesson, all right? We found the eigenvalues and the eigenvectors for this matrix already is the same one. So I'm using the same one to save time because I don't want to repeat that. So we already did this. So I'm just going to copy down the results from that example. The eigenvalues of A are lambda 1 equals 2 and lambda 2 equals negative 1. The corresponding eigenvectors are, oops, let me keep the notation the same. The corresponding eigenvectors are, so the eigenvector for this one, it was 1, 1, and the eigenvector, oops, and the eigenvector for the other one, we found it to be, for negative 1, we found it to be 1, 4. All right, so that would be the first step. Find the eigenvalues and eigenvectors, and once you have that, really, again, it's over. We can immediately write down the general solution. So the general solution is x equals c1 e to the lambda 1. So I'm just going to copy the formula in general first. T x1 plus c2 e to the lambda 2t x2. So now writing these things, we know all of it. So lambda 1 is 2, so e to the 2t, and x1 is 1, 1, plus c2 e to the lambda 2, which is negative 1, so this is going to become negative t, and then x2, which is 1, 4. And that is it. That is it, folks. That is the general solution of that. Now, I'm going to make just a comment about this. Um, you could rewrite this a little bit if you wanted to. My paper, I'm going to leave it like that. But you could just combine this into like a single vector. What would that give you? That would give you C1, and then you can distribute this. So you would get multiply e to the 2t by that and that. So this would be e to the 2t, e to the 2t, plus, and then this distributing this one, this is going to be e to the negative t, 4 e to the negative t. Okay, and this is like, and then we can continue. So this is going to be, okay, so this is going to be c1 e to the 2t plus c2 e to the negative t, and then c1 e to the 2t. So I'm just distributing here and then here and then combining. And then this is 4 c2 e to the negative t. Okay, and that means that this is x1 using the old notation, okay? x2. If we had written the system using x and y's, as I showed you, you get some books do, then that would be x, and that would be y. And no, it has to be the same C1 and C2. This is the proportion, the relationship here needs to be kept. Okay, so that's it. We're just gonna leave it like this though. You could unravel that, okay, and just figure out what the functions x1 and x2 need to be. If you were asked what is x1 and x2, then you could just simplify it into a single vector, and then x1 will be the top, x2 will be the bottom, if you had to do that. Okay, so we're just gonna leave it like that. So that is it. Okay, now let's do another example. This one we're gonna do it from scratch because that's not a matrix we have already uh, tackled. We haven't found the eigenvalues of that in any example. So let's start with that. So we're going to call A 1, 1, 4, 1, and we're going to find the eigenvalues. The eigenvalues of A, remember you have to solve the equation determinant of A minus lambda I equals 0. And the shortcut is that this is just the determinant of the matrix that you get when you subtract lambda across the main diagonal. So this is 1 minus lambda, 1, 4, 1 minus lambda equals 0. Now when you find the determinant, that is going to be 1 minus lambda squared, because 1 minus lambda is repeated, then minus 4 equals 0. Continuing over here, that would mean that 1 minus lambda squared equals 4, moving the 4 to the right, and then taking square roots, you get 1 minus lambda. I guess I don't need the parentheses once I take the square roots. 1 minus lambda equals plus or minus 2. You take square root of both sides, you get plus or minus 2. So that means there's two possibilities. 1 minus lambda equals 2, or 1 minus lambda could be negative 2. So this one gives me, if I move the lambda over here and then the 2 to the other side, we get 1 minus 2 equals lambda, or 1 plus 2 equals lambda. So this one gives me lambda equals negative 1, or lambda equals 3. And those are the two eigenvalues. Okay, I'm going to call this one lambda 1, and this one I'm going to call lambda 2. So we are halfway done through the problem already. It only took us like 2.5 minutes. So these are quick problems. I mean, they don't take forever like some of the Laplace transform problems. All right, so that's good news. And then now we're going to find the eigenvectors. So eigenvector for, let's say, lambda 1 equals negative 1. Once we find these eigenvectors, we're done. We can immediately write down the general solution. So now let's find the eigenvector for negative 1. Remember that means we need to find a vector v1, v2 such that a v equals lambda v. Okay, spelling out what that means, we know what a is 1, 1, 4, 1, v is v1, v2, lambda in this case is negative 1, so negative v1, v2. Okay, now multiply here, 1 v1 plus 1 v2. So on the top you get 1 plus v2, and on the bottom you get 4v1 plus v2 equals, distributing the minus, negative 1, negative v1, and negative v2. So you would get this system making the top entries equal to each other and the lower entries equal to each other. V1 plus V2 equals negative V1, and then 4V1 plus V2 equals negative V2. And remember, these actually do give you the exact same thing. Both of these equations do give you the exact same thing. If you were to move the V1, this V1 to the left-hand side, to the right-hand side, you would get V2 equals negative 2V1. And if you were to move this V2 to the other side, you would get 4V1 equals negative 2V2. And you see that if you divide this second equation by 2, you would get exactly this one. It's written like backwards, but you get the same thing. So that is the relation between V1 and V2. So that means our vector V is going to be V1, V2 equals, now V2 equals negative 2V1. Factoring out the V1, you get 1, negative 2. So that means the eigenvector, the corresponding eigenvector that we want to use is 1, 2. Remember that any multiple of this also works. This is just kind of like the simplest. Any multiple of these would work. So particularly if you multiply this by negative 1, you could have also used negative 1, 2. That also works. Any multiple that is not 0 works. So that gives us the corresponding vector for lambda 1. And now we find the eigenvector for lambda 2. Okay, now let's find the eigenvector for the other eigenvalue. So I'm going to continue this another page. So the other eigenvalue was, so find the eigenvector for lambda 2, which we found to be 3. So as before, we're just going to find, so letting V equals V1, V2, we're going to find V such that AV equals lambda V. Okay, so the matrix was 1, 1, 4, 1. And then V is V1, V2 equals lambda. Lambda in this case is 3, V1. Okay, so let's just multiply. So this is going to be, what is that? V1 plus V2, and then 4V1 plus V2 equals 3V1, 3V2. And then setting the tops equal to each other and the bottoms equal to each other, you get this system. But again, remember that both equations really are going to give you the same thing. And you can work with either one, whatever seems easiest. So the one that looks easiest it would be the first one because the numbers are smaller. So if you just move the V1 to the right hand side, you're just going to get that V2 equals 2V1. And that is the relationship between V1 and V2. So then that implies that V, which is V1, V2 is V2 equals 2V1, and factoring out the V1, you get 1, 2. So that means we can use this vector 1, 2 as the basic vector, eigenvector. Okay, and now we're done. Now we can write down the general solution of the system. The general solution of the system is going to be x equals c1 e to the lambda 1. Lambda 1, our first eigenvalue was -1, so negative t. X and then x1, this x1. So 1, -2, corresponding eigenvector. Plus c2 e to the lambda 2. Lambda 2 is 3, so 3t, and then the corresponding eigenvector, which is 1, 2, and that is it. If you wanted to unravel, but remember you could always simplify this and write it all as a single vector, and then the top would be x1, the bottom is x2. That would be the two solutions, the two functions that satisfy the system. Now I would like to do an example where we have an initial condition. So I want to work this one out so that you see how to handle an initial condition. Okay, so start. Let A be 5, -1, 3, 1. That is the matrix of coefficients. Then we find the eigenvalues for A. So that means we need to solve determinant of A minus lambda I equals 0. And this is just subtract lambda across the main diagonal. So 5 minus lambda 3, -1, 1 minus lambda equals 0. Now, finding the determinant, it would be 5 minus lambda, 1 minus lambda, minus 3 times -1, so that would be plus 3 equals 0. Now, FOIL, this would be 5 minus lambda minus 5 lambda minus lambda plus lambda squared plus 3 equals 0. Now, collect like terms. Write everything in order. Lambda squared, and then that would be minus 6 lambda plus 8 equals 0. Solve this quadratic. Either use the quadratic formula or factor. This one actually does factor easily. Lambda minus 4, lambda minus 2. So that means one eigenvalue is lambda equals 4. The other eigenvalue is lambda equals 2. Okay. Now you find the eigenvectors. So let me start with the eigenvector for lambda 1. Now I'm going to skip ahead because I already illustrated how to find eigenvectors. I just did one where I went through the process. So in order to make this quicker, I'm going to just tell you what it is. So if you go through the process, maybe you can stop the video and find the eigenvector yourself. That will help. You should be getting the same thing as I do. Remember that maybe you don't get the same numbers, but you get a multiple. As long as you get a multiple of what I get, that would be fine. So if you go through the process, and again, try to do it on your own, you're going to find that the corresponding eigenvector for lambda 1 equals 4 is 1, 1. And the eigenvector for lambda 2 equals 2, do that one as well. You're going to get 1, 3, or a multiple of that. So those are the eigenvectors. So that means right now we can immediately write down the general solution of the system. The general solution is x equals c1 e to the lambda 1. Lambda 1 is 4. T times the corresponding eigenvector, 1, 1, plus c2 e to the lambda 2. Lambda 2 is 2. T times the corresponding eigenvector, which is 1, 3. So that right there is the general solution of the system. We have an initial condition, so that means we need to figure out what C1 and C2 are. The initial condition is, so let me show you real quick. Initial condition is when you plug in 0, you get 2, negative 1. So the initial condition is when you plug in 0, on the one hand, you get 2, negative 1, but we already have a formula for x, so we can just plug it in here. If you plug in here 0, you get e to the 0, which is 1, so you would only get c1, 1, 1, and that is also 1, so you get c2, 1, 3. Alright, so from there, we're going to figure out what c1 and c2 need to be. Okay, so I'm going to continue another page. So we're going to now figure out what these c1 and c2 need to be. So let's unravel this. So simplifying, we're going to get 2, negative 1 equals, and then just distribute the C1. This is C1, C1 plus C2, 3, C2. Okay, distributing the C2 here. And then simplify further by combining these. This is C1 plus C2, and then C1 plus 3, C2. And now we're going to set the tops equal to each other and the sec and the bottoms equal to each other. So you get the system. And I'm going to write the variables on the left. So C1 plus C2 equals 2. And then C1 plus C32 equals negative 1. And this is a system of linear equations of the type that you learn in college algebra. So I'm just going to subtract. So multiply the first equation by negative 1. You're going to get negative C1 minus C2 equals negative 2. C1 plus 3C2 equals negative 1. And now you can add down, and the C1s disappear, and this gives you 2C2 equals negative 3. So that means C2 equals negative 3 halves. So C2 equals negative 3 halves, and once you have that, you can plug it back in here and figure out that C1 equals 2 minus C2. So we just move the C2 to the other side, you get C1 equals 2 minus C2. But we just found that C2 equals that. So 2 minus negative 3 halves, that is the same as 2 plus 3 halves. And then finally, common denominator would be a 2. So it would be 4 over 2, and then it would be 7 over 2. So C1 equals 7 over 2. And now we have found C1 and C2, so we have solved the IVP. So a particular solution of the system is x equals C1. C1 is 7 halves e to the 4t 1 1 plus c2 is negative 3 halves e to the 2t 1 3. Okay, that is the particular solution.